Thank you, Michael. I appreciate those kind words. Good morning, everyone. You know, it's good to be here. At my age, it's good to be anywhere, that's for sure. Anyway, this morning it's my pleasure to introduce a keynote speaker, and I appreciate the stage program committee for offering me this opportunity. Our speaker holds a BS and MS degree in civil engineering and is a master trainer and a contract operator. He has more than 45 years of experience in civil, transportation engineering, construction, and 32 of those years with the Federal Highway Administration, which began in June 1976. During his career with the Federal Highway, some of his special duties were transportation departments throughout the United States, were development of training, national demonstration programs, development of manuals, technical assistance. I'm sure many of you have benefited from these manuals and training. I first became acquainted with him early in his career when I was geotechnical branch manager for the Kentucky Transportation Academy. During this period of time, the state-of-the-art of geotechnical engineering was just beginning to get off the ground. In my opinion, the FHWA, under his leadership, was responsible for providing more technical assistance to the geotechnical field than any other agency. I am sure if you've attended the stage in the past, you are very familiar with his many presentations. He has provided consultant services on approximately 1,000 civil construction and business-related projects in all 50 states, Middle Eastern countries, and Australia. Some of his favorite projects are Boston Central Arterial Tunnel, Ravenel Bridge in South Carolina, Honolulu High Capacity Transit System, and Forest City landslides in South Dakota. He has received many awards, which include ASCE, Opal, and NAP, FHWA Engineering of the Year, FHWA Administrative Award, and awards from PDCA, ADSC, and TRB. He has been married for 49 years to a delightful lady named Bobby, who is in attendance in this conference. They have 2 daughters and 7 grandchildren. Legend says that he was a distant cousin of New York Yankee great Joe DiMaggio. Please join me in giving my friend Jerry DiMaggio a warm welcome.
Good morning, everybody. Good morning. Give me a minute to wake up. Here we go.
How's the audio? Not too much, is it? Okay. For those of you who've heard bits and pieces of this presentation in different venues, I apologize. I did not choose the topic. Some of my very good friends who are in attendance here selected the topic for me. Hopefully it'll be entertaining, and those of you who've heard me speak before, you know, one of my mottos is you cannot kind of communicate with anybody unless you have a little bit of levity as well as technical matters. I've got 38 slides to share with you today, and we'll go along. Can you see, hopefully, can you see the white font? I guess that's a little concerning to me. Okay, you okay? Men's amends, huh? All right, that's a little bit of Italian. We don't have many backgrounds. It shows up well on the computer, but I think we lose a little bit in the translation. So if you look at the title, it's a bit long-winded as titles go. I've been around for quite a while, and Henry, thank you for that excellent. It's quite an honor to be introduced by a long-time friend such as Henry Mathis, who's quite an accomplished geotechnical engineer in his own right. I'm a little embarrassed he's worked a bit longer than me, and I had a note slipped to me and ask if who was older, Henry or I, and I'll leave that to your imagination. Anyway, I did not come up with that, Henry. We'll beat up on that person later. So I've been around for a while. I've done a lot of very interesting things. I want to call your attention in particular to the last bullet, if you can read read that well here. I think growing up in Brooklyn, I was quite naive in terms of being exposed to the world. Those of you who know anybody from New York City and being an expatriate, I can say this, is that they tend to think the mecca of the universe is revolved around Manhattan. And I learned very quickly in my professional career that that is totally incorrect. And one of the great things of engineering and engineering, geology, and geology is that we have an opportunity to meet many people of different religions, different cultures, and we become enlightened and educated through those experiences. I consider myself blessed by God to have that opportunity. So I just want to kind of give you that note as we go along here. I'm going to hit a couple of topics, and Henry has introduced me in previous presentations over my 46 years, or some odd 40 years of association. I tend to chastise the profession as we go along here, so we'll leave that to, I've tried to soften that chastising a bit by referring to it as future challenges. And there's a little bit of disappointment I'll share with you. Don't take it personal, any of you. It's not intended to be personal to this audience or any individual. So we'll talk about what's happened or what my career, and this is my view of the world. I'm going to reflect on advancements in geotechnical practice. That'll be the bulk of the discussion in my time that's allocated today. I'll talk about some disappointments. And whenever we have a disappointment, you'll see some of repetition in that as we go forward. You'll see some of the same bullets, because when we have a disappointment that presents a challenge to us as a profession, and we can move forward and to do much better than we've done in the past, and those that are going to succeed us as we go along. In your wildest imagination, when you were growing up, perhaps some of you playing in dirt piles with little trucks and tractors, you probably never imagined in your life that you would dedicate your career to working with geomaterials. Even as you graduated with a doctoral, a master's, or a PhD degree, you probably did not fully appreciate that you were dealing with the most complex material on the face of the earth. And when I say material here, I'm referring to intermediate geomaterials, rock and soil. And there are many sub-definitions, as we all know in this audience as we sit here. You probably never thought about that. Two things. You never thought about dedicating a large part of your professional life and your personal life to this topic, and you never fully appreciated the complexity of the material that you were going to be dealing with. So as we go along here, we'll talk about some things as I reflect them back when I began working after graduate school in 1973 until the present, things that have changed and things that remain the same. If we go back to 1973, the mainstay geotechnical exploration tool was the standard penetration test, and as we well know, the standard penetration test is still well embedded into every geotechnical exploration that we undertake. Now, is that good or bad? I think as long as we fully appreciate, and in some cases, I have to admit, we don't fully appreciate the limitations and the benefits of this tool, that's just fine. Of course, some things have come a long way that help us further investigate the underground. And I'm just showing, I can't, in the time allotted, touch on everything that's changed. Many of the in situ tools, and you see the standard penetration test in this slide on the immediate left, that's pretty much remained the same. Its limitations and advancements have been well known for decades and haven't changed very much. But we see some other tools that have been introduced and gradually have become mainstreamed into practice. Tone penetrometer has been around for about 60 years, depending on how we count the beginning entry. And I've observed from afar that the acceptance of that particular index tool has become much greater progressively in really around the world, but certainly within the United States of America, slowly. Now, what's the negative side of this? I think often I catch myself, and I'm still quite active. I work usually, I'm told, about 70 hours a week, and my wife Barbara can attest to that. So I'm going to cut my time to 3/4 time, so that our CEO Board of Directors group told me that means I'm not going to work on Sunday afternoons anymore. So, What do I see in terms of in situ testing here is I think we've forgotten that all of these tools have to be indexed to fundamental soil and rock mechanics, depending on the tool that we're talking about. And we sometimes see on projects, unfortunately, that these great tools are misinterpreted as being foundational tools. And I mean foundational not in the sense of a structural foundation. I've taken a clip from the Asheville Bridge Code. Some of you are familiar with that. It weighs 14 pounds, 8 ounces. When you have a code that you count by weight, you know it's got to be impressive. It's the only code that I'm aware of, those of you not familiar with it, that has been updated with the exception of 1 year since the mid-1930s. It has an excellent coverage today, which it did not have historically, on geotechnical exploration, which is what the focus of this slide is. It also covers the design and analysis of geotechnical features across the board. Kind of, since it's a bridge code, it doesn't deal on the earthwork side as well as it does on retaining structures. The key thing that this slide is intended to represent, which is an advancement in my view during my career, is the last bullet that's highlighted, and that is the selection of design and construction parameters. We're champions collectively at collecting factual data. We don't really do as good a job, but now that it's codified, we can lean on that as we entice customers to spend a little bit more money and let us do a better job on the summarization, the analysis, and the selection of the properties for design and construction. You notice I said design and construction. Rock, we've discovered. Now, my geologist friends in the audience don't take offense to this, but I think the geotechnical engineering community today has much greater respect and appreciation for the sophistication of the rock that we deal with, in particular for drill shaft foundations and micropiles. We need to understand rock. And again, an enlightening moment for myself was the fact that rock comes in a variety of strengths. And I use this index cliche often. We typically work with cast-in-place concrete 3,000 psi, precast concrete 5,000 psi. We have rock by definition, which begins unconfined compressive strength by definition above 1,500 psi. And the maximum strength, as some of you well know, is in excess of 50,000 psi, in order of magnitude greater than our typical precast concrete. By better understanding rock, we've become more efficient in optimizing our structural foundations. If you go back during my career again, my view of the world is that we were somewhat ignorant in terms of the selection of design and construction properties of such a complex material. Now I know I may put shivers down some people's spines, but we have to say a little bit about the advancements in terms of understanding the sliding scale, and this is an LRFD, load resistance factor design table, that is equating different evaluation methods for the prediction of geotechnical axial resistance of a deep foundation. And it's a sliding scale. If those of you may remember, you older people may remember something, the mainstream use of driving formulas. And you see that the driving formulas in this case vary from 0.1 to 0.4. And you see if I do a static load test, which I'll speak to a little bit further on, I get to use a resistance factor of 0.75 to 0.8. For those of you who are not familiar with LRFD, the higher the resistance factor, the less uncertainty associated with the design. We can optimize our designs and our construction features better. Now, the purpose of this slide is not to give you a tutorial on the mechanics of LRFD and resistance factors. The purpose of this slide is to demonstrate an evolution which has occurred over time gradually, perhaps not with a premeditated approach. The fact that we now numerically can equate factor of safety or resistance factors to the confidence level in which we have for the prediction of resistance, or the counter side of the equation is for the estimation of what the load. That is a monumental step forward for the geotechnical community. When I say geotechnical community in this discussion, I'm meaning it to be all-inclusive geologists, engineering geologists, and geotechnical engineers. We also have gained respect and gained a better understanding of something that in LRFD parlance is referred to service limit state design. I'm going to focus on the right-hand side of this slide. So we well knew back in the 70s and the 60s about slope stability analysis and knew how to do that by the arduous task back in the 60s of doing it by hand computation, and now some beautiful computer programs that we'll talk about in a little bit. But the purpose of this slide is focused on deformation. In historical practice in civil engineering dating back hundreds of years, the focus of our designs was based on strength-based design of civil engineering features. It took us quite a while, if you think back to hundreds of years ago, and the evolution of beginning to have a conversation with our counterparts, the structural engineers, to speak intelligently about tolerable deformations, both in terms of horizontal and vertical elements. So no longer today, some of you do not deal in the highway business per se, at least exclusively. Now today, using the AASHTO LRFD code, we can have an intelligent conversation, and in fact a very necessary conversation with our counterparts in the structural discipline, and say in fact that some deformation, even on a deep foundation, is in fact necessary and appropriate so long as it's held to appropriate boundaries and the performance criteria of the particular feature that we're dealing with. What has changed? So I'm kind of jumping topics here. If you're with me, you get the drift of this. What has changed? This is a Kentucky bridge. This is one of the Kentucky Lake bridges, which obviously no longer exists. This is one of the main spans. Fortunately for the cabinet, and I had the luxury of being on one of the teams working on the new bridges, Kentucky Lakes and Lake Berkeley, is that the purpose of this slide, in terms of the emphasis that we now have to deal with, either by climate change or by whatever definition that you choose, are demands on our foundations for infrastructure features. By the way, I want you to remember, the only infrastructure feature that doesn't have a foundation is a boat. So anything we build has a foundation. We should be very proud of that as the geotechnical community. Extreme events, those of you who haven't dealt with this, can eat our lunch relative to controlling the foundation demands on a project. Some of you may be familiar with the Tappan Zee Bridge in upstate New York. Approximately, engineers estimate, $4 billion bridge, one bridge, $1 billion in the structural foundations, 25% of the total cost of the structure. Construction point concept. This might be a bit unfamiliar with you, and it's tied to the serviceability designs that I spoke about a little bit before, is that when we engage in conversations and we do our computations from a geotechnical point of view for prediction of horizontal and vertical deformations and the related associated times with that, it's important that we converse with the structural specialist either on the building side or on the horizontal side of the business, the bridge side, and we have a discussion of the development of the deformations as the load is applied. You see my little cartoon on the right here is a bridge pier, and the concept of this slide is when we have a discussion related to tolerable deformations, we should be speaking about what is acceptable from a post-construction performance criteria and not the total load that's applied to the foundation. In the case of a pier such as you see here, I don't really care what happens until I put load D on. And then I should engage in that conversation with the bridge specialist and then say, what can we accept, 1 inch, 3/4 of an inch? And oh, by the way, please, bridge engineer, don't tell me the Valentine sign of 0 deformation. You old people know that Valentine was not a bourbon, it was a beer in New York City. Our computational methods have advanced tremendously. They even look pretty, such as this finite element analysis that's there just for eye candy. But a word of caution to the younger specialists that graduate with either an MS or a PhD degree is that we must not forget that we have to be able to run some reality analysis, perhaps on the back of a cocktail napkin or back of a coaster. That's imperative. I can't tell you how many times, and maybe it's growing up through the hand computational method phase, I could look at a computer analysis and say, something does not look right off the cuff. And I'll do some quick and dirty analysis, and believe me, I'm a Brooklyn guy who grew up from a blue-collar truck driving family, and I ain't very smart. So I must have learned something in 46 years. Balance computational methods that are simple with sophisticated, beautiful analysis that look like this. That's the message. We've come a long way, baby, with this stuff, but let's not forget our roots, or roots, whatever you like. Okay, so another topic. Just like Rodney Dangerfield, the great Jewish comedian, often said, I don't get any respect. Well, in the early 1980s, retaining walls were not on anybody's radar screen to the extent that they are today. So this is the, I believe, still the tallest mechanically stabilized earth structure in the United States, Seattle-Tacoma Airport. I've not been involved with all of these photos that I'm showing you, but every time we turn around, we see a retaining structure. And one of the cliches I use, and don't take offense, my good friend Larry and the other Florida people, I always say if I'm in Florida and I throw a rock in any direction, and I'm lucky with my rock throwing, I hit two things, an MSE wall and a geotechnical engineer. If you get a lucky bounce. So sincerely, we might have a major interchange on one of our national highway systems, such as the structure that the project that was just discussed. You look at a major project like that, it is not an inconceivable thought that you might have in excess of 1 million square foot of retaining wall on that single project. I-395, 495, 95 in Northern Virginia has 1.25 million square feet of retaining wall, one single interchange. So retaining walls have gained respect. There's also many different types. We won't get into that. We don't have time for that. Project up in Cleveland, Ohio. I did work on this project. And the message here is that our materials have changed. On this particular project, and I apologize if the white is washed out in the upper right here, but the message here is we have moved to higher strength materials, and this is steel piling, of course, but I'm talking about allowable stresses on timber. We can't change timber that's made by God above, right? It's not a man-made product like steel or cement or concrete, but we've made enhancements in terms of allowable stresses we apply. In the case of steel and concrete, we've enhanced their strength. We can't, when I was growing up, when I got out of graduate school, steel pilings were 836 steel. We didn't have the advancements in load testing that we have now. And a design stress on a steel H-pile would be 3 to 4 KSI out of 836 steel. By any stretch of the imagination today, if you saw such a design stress in those sections, you would think those designers were insane. This is 80 KSI steel on an H section. And just using that, we could go on and talk about using 8,000, 9,000 PSI, 8,000, 9,000 PSI concrete for precasting on piling. Some special things that we have to look at when we use these higher strength materials. Now, that's by strength of materials. What we've also seen is tremendous dimensional changes. When I was growing up in the business, started my career in New York State DOT, before I spent 2.5 years in the training program and then got laid off with success in federal highways, we were dealing with 8-inch piles and 10-inch piles and 12-inch piles, and we still do to some extent. But the reality of the matter is, we often hear about 10-foot diameter drill shafts. We hear about 10-foot diameter driven piles, 4-foot diameter driven piles, 4-foot, 6-foot, 8-foot, 12-foot diameter drill shafts. I'm currently working on a project in New Jersey, 300-foot deep long drill shafts, 10-foot diameter. Back 45 years ago, these were things that did not exist. And those of you who are new to the practice, whatever that means for you, you just don't fully appreciate, you can't, because we're all dated and biased by the time that we ended our careers, things that have changed over a period of time. Things are constantly changing, that's why we're not as aware of it as we might think we need to be. What has happened in 45 years relative to driven piles is we've learned the meaning of drivability. And through the great developments of a number of really smart engineers at a number of universities and public agencies, we no longer, or should no longer, have the situations you have illustrated on this slide. You have a closed-end pipe pile on the left. We have an H section. Both of these piles have been withdrawn. If you look at the top, and you can't see the H section very well, you would fully appreciate from the ground surface, you would be that dumb and happy and saying, that pile looks perfectly great. I have had some structural engineers, and it happened to be actually a chief bridge engineer in Kentucky that I recall. I can't remember his name right now, but he was a great kibitzer. Kibitzer in New York Yiddish means kidding around. But he would look at the pile on the left and he'd say, Jerry, said, so what? I got more skin friction and you saved concrete. Now, I'm seldom at a loss for words, but I have to admit, I did a Ralph Cramden, a hama. I didn't know how to respond to that. So certainly, to the message here, we should no longer, thank goodness to the tools that we have today, have these kinds of problems that were chronic in the 50s, the 60s, the 70s, until these tools were mainstreamed into practice. Drill shafts certainly had a long history before they became mainstreamed into practice. And in my career, the linchpin for the federal government in terms of becoming more interested in drill shaft research, which is still going on, and Silas will speak about that later today, was the collapse of the Schoharie River Bridge in New York State on the Thruway. That occurred in the 80s. And that led us to better appreciate the importance of the foundation, and it reestablished, perhaps excessively established, the focus that we have on scour analysis related to our structures. So back in the 60s, as you see in this little cartoon that's here, we, in the mainstream areas, Texas, Chicago, etc., we belled our drill shafts. In fact, we still do that. Why did we bell drill shafts? I'll answer my own question. Because we had no confidence at that time in the skin friction resistance of what a shaft could provide to us, both in soil and in rock. Now, by today's learning knowledge base that we have, the amount of information we've accumulated over 45 years, we very confidently and very routinely will design straight-sided shafts, in many cases where they're totally designed for skin friction without the contribution of end bearing for a variety of reasons in some cases. And shafts are pretty simple. Anybody could do this. You drill a hole, you put some steel in the hole, and then you chuck some concrete in. How can anybody screw that up? How can you ever have a defect or a discontinuity? Whatever you want to call it by fancy terms. Well, some snickering, of course, and I'm being quiet here, is that we know that we've got some challenges. Some concrete engineers tell us when we take these shafts beyond 6 feet, we must be crazy expecting the concrete to do what we really expect it to do without extraordinary means to be successful with it. 300-foot deep drill shaft now, 10-foot diameter. I'm excited about that project, but I've had those before. I'm just praying we don't have too many problems. Micropiles. How many people knew that micropiles came from Italy? Pizza did not come from Italy. Spaghetti did not come from Italy. Micropiles came from Italy. Introduced and developed more than 60 years ago, post-World War II environment, it had a structural application before it had a geotechnical application. These are mini knee piles. We know a lot more today, and we routinely use these tools. I had the opportunity to work on the first micropile project that was associated with the highway industry, out in California. That was dating back to 1976, right when I had joined FHWA. And we looked at this. Back in those days, we would import a lot of technology, as we do today, from Europe and then also from the Far East. And we looked with skepticism at micropiles because it was something new. And we're engineers and we're naturally conservative, but nowadays we talk of it as if it's a household word. So that's the message I keep going to. Things have changed quite a bit. From the Woodrow Wilson Bridge, which I also had an opportunity to work on, an albino pile hammer, which is white after months of operation. Double-acting, hydraulic-driven pile hammer. Now, probably 1,000 different pile-driving hammers that we have available to us on projects that can do literally anything that we need to do. Flashback to the 1970s, our knowledge in terms of pile hammers as engineers was pretty puny. And the state of practice back then was there can never be anything that goes wrong with the hammer. The ram goes up, the ram falls down, I count the blow, the ram goes up, the ram goes down. We all know through measurements of pile driving analyzer, through wave equation analysis today, there are many things that can go wrong with driven pile hammers. The biggest challenge today for us as well as the contractors is to select the best tool for the project so everybody's happy. And of course, we don't want to have any new photographs of damaged piling. More blows ain't better. So not to shortchange the drill side of the house, we've got oscillators, rotators, we've got a vacuum cleaner, extraction tools, we've got all kinds of wonderful equipment that didn't exist 40, 45 years ago that allow us to do the things that we do today. I would not, in my wildest dreams, imagine that I'd work on a drill shaft that was 300 foot deep of that diameter 40 some odd years ago. And even if you designed it and you could build it, how in the world would you ever load test it? How would you provide your client confidence that those elements of such a size and such a load carrying capacity would be able to sustain the design loads that are applied? Well, fortunately for us, load testing has become a household word. In a study that I managed federal highways back in the early 1980s, which to me doesn't seem that long ago, but was quite a while ago. Do you know that there were approximately 20% of the highway departments at that time, this is 1983, 1985, who had never, and the word never, N-E-V-E-R, had never run a load test on a deep foundation element. 20% of the highway departments, right? It's about 10, depending on how we count Puerto Rico and the district. That's inconscionable. And those that ran load tests, running load tests to twice beyond the design load, that was heresy. Because once the pile failed geotechnically, it was no good anymore. We know that's a falsehood. So put that in the context of what we have today. We've got all kinds of specialty tools, bi-directional load testing, and I could go on and on and on for a discussion here that enables us to use the tools that we have today, be they micro piles, be they high-capacity driven piles, be they high-capacity drill shafts. Now, we're interested in one other side of the equation relative to geotechnical features, as I believe I coined that term a long time ago, is we have made tremendous advances in non-destructive testing and evaluation. Now, those of you who haven't dealt with this doesn't tell us necessarily quantitatively if we have a bad element. It's like an MRI. Everybody in their life goes through the experience of one MRI, and an MRI in a very simplistic layperson's terms is to say, I see something that looks a little bit different than everything else that I see. And then from that, we have a further investigation that requires some invasive evaluation. That's really, in a nutshell, what we have today relative to non-destructive testing. Now, what's changed? Now, when I was in graduate school, I took 2 geophysical courses, which is kind of unusual. I took, for a geotechnical engineer, I actually took 6 geology courses, undergraduate and graduate, but back in those days, the fundamental models are still the models that we use today, but what's changed as you look at this list and look at all the tools, the algorithms have changed, the sensors have changed, the data collection efficiency and analysis has changed, and oh, by the way, the engineers who are using them have also gotten a lot more astute in interpreting the raw data. So we've got lots of tools that we can evaluate. Load testing in the previous slide, and then in this slide, we're concerned about integrity because we're not Superman or Supergirl, and we can't see below the surface. If we look at geosynthetics, 1957 was a sideline outlet, a woven monofilament that was used as a 1957 Chevy seat cover, was introduced in the early applications of geosynthetics as an outlet for an excess supply in a warehouse. In the early 1970s, that was followed by the introduction of a product called Beatum that was introduced by Monsanto into the United States from France, and that was pretty much the introduction of non-woven materials. There was a needle punch non-woven, so we had a non-woven, we had a woven. So what does that mean today? That's me under all these samples. This has now grown to be in excess of a $1 billion annual business. It has over 100 civil engineering applications. We have over 600 products that are on the market. If we date back to the early introductions of geosynthetics, we would have never imagined that evolution and the acceptance and the problem-solving capabilities of these materials that are made of polymer. A lot has changed in 40-something years. Ground improvement. When I was at the National Academies after I retired from Federal Highways, I was the implementation manager for the Strategic Highway Planning Research Program, from everything from long-term planning through operations and systems management for 5 years. The only geotechnical project was a $3 million contract to develop something we now know, many of you know it in the audience, as geotech tools. And that crossed the line a little bit in terms of educating the community on something more than ground improvement, but it actually has 50 different technologies, and those are listed here in terms of a technology. I'm not very smart on compaction grouting. What information can I get from that? A little fact sheet, some photographs, some guidance on design procedures, QA/QC specifications. This did not exist 40-something years ago. Ground improvement was viewed as with skepticism, with the exception of perhaps wick drains. So, as an example of that, one ground improvement technology that we speak about is the family of grouting. And grouting is understood back in the 70s and the 60s that grouting is a technology of last resort. Right? I'm going to try everything else, and then if I can't succeed, then I'm going to look at grouting. And then how do you find a reliable grouting contractor? My friends at Hayward Baker, this is a true statement. I have had people tell me that when they ran into trouble back in that era and they needed grouting, they looked in the yellow pages. So this is like bail bondsman. You look AAA grouting, those are the first people that you call. So we've come a long way. This is a sophisticated, high-tech readout instrumentation box from a major I&M project. I'm being facetious here if you haven't picked up on this. This is 1976. This is down in Hampton Roads, Virginia. And this is readout device, state-of-the-art. And instrumentation back in that era was known to have redundancy intentionally installed in it, because even if you were meticulous and you were learned, you might expect a 50% success rate in geotechnical I&M work. Nowadays, if you have the right people and the right equipment, our expectation has become much higher. We expect 100%, maybe 95% of success with every single instrument. We don't include an extra 50% as throwaways. Plans and specifications have changed. When I was at New York State, if you were told that you were sent to the specifications section of the highway department, you knew you had screwed up. This was not a job you took or you were assigned to because you were an enlightened, up-and-coming individual. Don't take offense of any of you that worked in the specification section. I just 2 weeks ago reviewed a special provision for drill shaft project, different project than I referenced before. 45 pages in length. 45 pages in length for a drill shaft special provision. They've become more complex, they've become more litigious, and our awareness of the importance of plans, notes, special provisions, standard specifications to keep them as a primary communication tool between the designer and our construction staff and the contractors is an enlightening point that really wasn't fully appreciated by many 40 years ago and probably by some today. I heard Andy speak about different delivery methods. In different delivery methods, there's some good and some bad for that, and I won't go into all these methods. I mean, the delivery methods, P3 is really a financing method. CMGC, design build. Probably some of you all in the audience have worked on these different methods that we now, on a growing percentage, are dealing with day in and day out. Your risk change when you go from a design bid build project, if you're a geotechnical specialist, to a design build project. You've got to be a bit careful. Those of you in consultant practice, and because I'm old and I'm getting bald, people think I know something, so I do more dispute resolution work than I've ever done before. And I find that the geotechnical designer, or the designers on these schemes, really, in my opinion at least, absorb more risk. It's not a fair allocation of risk. So be very cautious if you're well versed in design bid build, and then you're moving over these other methods. I'm going to be here through tomorrow evening, so if you'd like to chat about anything. 45 years ago, we didn't appreciate one thing that's become a household word, and that household word is risk management and asset management, or risk-based asset management of geotechnical features. And this is eye candy slide here of a rockfall problem. We were well aware of these liabilities, but if you refer to geotechnical features as liabilities, you ain't going to get no money. So we have to talk to them about, we have to think of them as assets, we have to present them as assets. What's the design life of an embankment? I was asked that question, and I have to admit I couldn't come up with a very good answer. So we're going to see more of this. There's some great studies that have been done, NCHRP, some federal highway work that focus on geotechnical features to help us out here. So quickly, I've got about 5 minutes left. We talk about technical disappointments. I'm shifting here. This was the short side of the presentation. I've only got 38 slides. So I really, as a naive young engineer, I thought that it was easy to sell new innovations. And shallow foundations are certainly back in the 70s were not a new innovation. But I'm still amazed and disappointed today that we haven't made more kind of headway into the further utilization of shallow foundations in the appropriate areas. Pavements, I think we've made some headway in particular using geosynthetics. If you work for, we have a number of geosynthetics exhibitors here, and repeating again, make sure you visit those people, the ones that are here and the ones that are not here. But in pavements, I think the dream in 76, like every pavement would be like a landfill and have 13 layers of geosynthetic in it. Well, we're gradually making headroads, other than separation application is pretty well embedded. We really haven't begun to fully utilize geosynthetic in pavements. And I was kind of naive, being from Brooklyn back in those days. Tolerable movements, I thought that'd be a piece of cake. Now, why have we failed relative to getting the structural community to better embrace tolerable movements? Because if you're asked a single question, you won't be able to answer it. Jerry, you told me the differential settlement at these two substructure units is going to be 1.5 inches. How confident are you in that prediction? Have you done a parametric study? 98% of this audience can't answer that question. We've seen advances in soil structure interaction, but we're not quite there yet. Quality of construction and monitoring, don't take this offensively, but I think has gone downhill in the last 4 decades. Doesn't mean our inspectors do not, excuse me, educate people. Take a look and focus on the last bullet. I hear this, not from the geotechnical people, certainly, but a growing question raised by your clients is whether geo work is really adding value to the project. And maybe they chose the wrong geotechnical specialist. Some professional disappointments. There's a growing number of people in the business, and I'm aging myself, but I think as younger people view engineering as a job rather than a profession. If you're blessed with good health and you like the field that you're in, you're going to work at this for about 50 years, or if I look at my good friend Henry here, perhaps longer. It's a profession, and you've got to be concerned and contribute to your profession. If you want a job, I can get you a job with my brother-in-laws. They're out on work release driving a truck. I don't think we really fully embrace this concept of a holistic view of geotechnical involvement on a project. Pardon me. I don't think we communicate as well as we could, both written and oral in general. I don't think we exhibit the leadership and team building skills that geotechnical community can really be involved with on projects. Look at the cost and the risk associated with the elements that we contribute to. We should be more aggressive is the word that comes to mind, perhaps not the best word, but we should be exerting more leadership than I think I see. Gone, which were prevalent through the 1970s, are full-service geotechnical firms. That's a danger to the profession. You could deal with a designer who's been in practice for 30 years, who's never been in a geotechnical lab and never been on a drill rig. That's a problem. That's a huge problem. And then there are fewer and fewer research dollars that are available. I still have the green light here. I'm almost finished. Bear with me. So now to close this out on a positive note. There's some grand challenges and wonderful opportunities, and I've written some of these in a negative fashion, but you can twist them around because this is the smartest crowd I've had since last week. So I mentioned a number of times this disappointment and tolerable deformations, but there's work that's ongoing that you need to be fully aware of and contribute to that will help us serve the public and serve our clients much better relative to optimizing. There's a word not often used. I noticed the word is used, optimized, on introduction to one of the presentations. Mainstream application of cell structure interaction. We've got to improve construction quality because I've been in a number of meetings from the design side and say, we don't trust construction. So we're going to beef up the design to overcome the perceived imperfections in construction monitoring. We can't do that because we can't afford to do that, and it's not the right thing to do. Always demonstrate value to the client. If you whine and moan to me and say, I asked for load tests and I asked to be involved with construction monitoring, and they said no, what I'm going to tell you is look in the mirror tomorrow morning and tell that person they need to be a better salesman and communicator, and if that still fails, then perhaps you want a different client. So, from a discipline point of view, and again, these are my opinions, you could beat me up later on, why do we not exceed in some of these areas I mentioned previously? I think we, like other technical disciplines, behave in a cylinder of excellence, or in a negative fashion, a stovepipe fashion. We generally tend to be reactive rather than proactive as we see evolutionary things like design build, as CMGC. I've been in many meetings on these major projects. I won't have a geotechnical specialist at the table, but yet it'll be a meeting of 50 or 60 people. We've got to better understand and have an open dialogue and be able to speak the lingo of the other disciplines. So when you talk about seismic, when you talk to structural engineers, like us, they all have their own vernacular, and we need to understand that, and we need to respect it, and we need to communicate better. That's one of the beautiful things, by the way, of LRFD. It forces that communication. So what are the causes of some of these problems? You see those listed here. We've got lots of stuff. We're so busy doing what we're doing, sometimes you can't pick your head up. Now, it's important that we play this role and we make some changes because it's going to have a direct impact on our work, not only in the interest of our work, but our ability to turn a profit, our ability to serve the public. And we've got a lot at stake here if we're going to be successful as we move forward. I'll probably work, if God has blessed me, for another couple of years, going to part-time here in January. You younger and mid-level career people, you're the people that it's going to affect. You're the people that it has to change. So I want to thank you for your attention. I still have the yellow light. Hopefully this was informative, and I'm really honored to be your keynote speaker. Thank you very much.